Good day, chemistry students. Today we're going to look at heating curves. Okay, so we should be able to, by the end of this, explain the plateaus in heating and cooling curves, that including IMFs, how this relates with IMFs, and exothermic, endothermic. Those are terms we're going to use in this. You should also be able to define melting and boiling points in terms of intermolecular forces and particle size. All right, so this is a typical heating curve that you will see as we go through this unit. So you have the temperature on your y-axis, time on the x-axis, and as we increase the temperature of, in this case, ice as a solid, you get to 0 degrees, which of course is the melting point of water, and you get to a plateau where both solid and liquid are present. And then so you can notice that temperature isn't increasing while you're at this point over a given amount of time. And then at a certain point, when all solid disappears, then all of a sudden you have a liquid. Okay, so we want to focus on that plateau in particular. So the heating plateau, minimum amount of energy is needed to overcome intermolecular forces. So that's what a heating plateau is. It's the minimum amount of energy that's needed to overcome those forces that are holding the molecules of ice together. So this is actually an endothermic process. It requires heat to be put in. That is endothermic. So all added heat is used to overcome these forces, not increase temperature as kinetic energy. So that's why our temperature stops increasing at this point. Once we get to here, then temperature just stays the same basically, and we're going to look at this a little closer in the next slide. And once all that ice has melted completely, then the temperature of your liquid can start to increase again. So this is the plateau, this flat part, just like a plateau in, the desert or wherever. Plateau just means a flat area, right? Okay, so this plateau ends when all of the particles have changed phase. So looking at it a little closer here, so what actually happens, it's not completely flat. If you were to zoom in on this to the, on this scale, to the microscopic level, what you would actually see is temperature increasing as we go, hits 0 degrees, starts melting, but what happens is you get that a little bit over 0 degrees, and then that substance is heated up, and then you get energy that is taken to break those IMFs. And that energy, uh, because that energy is being used to break those IMFs, that means your temperature is going to drop back down to 0 degrees. And then again, you're heating it up, right? So you got some heat source, so there's energy being put in, and then that energy uh, breaks those IMFs, and therefore it cools that down again. And you keep having this same process happening over and over again until you get to the point where all of the solid disappears. Now, the length of this plateau depends on, of course, how much solid you have, how fast you're heating it up. There's a bunch of things that could vary how the length of this plateau, but it will continue until all of the solid disappears. At that point, then the energy can be put into heating up that liquid at that point. So the cooling, I was going to actually, sorry, I had an analogy for this. So um, imagine, and it's kind of like you've got a pot of water on your stove, right? So you're boiling, or you've got ice in there, sorry, a pot of ice on your stove, and you're heating it up, and that water is melting, um, and it gets to the point. Actually, no, sorry, I was going to say a pot of boiling water. or hot water, whatever the case. It doesn't really matter. Hot water, and you put you drop an ice cube in, and that temperature would be increasing, and then all of a sudden you throw an ice cube in, and it drops that temperature down. And then once that ice cube's melted again, then it starts heating up again, and then drop another ice cube in, and it takes that energy away. So that's kind of how you could think of that. That because that energy is being used to break those IMFs, it's taken away essentially. So any of that heat that was put in, it just gets absorbed. All right, the cooling plateau, it's the exact opposite process. So particles lose energy and slow down, so then they are pulled together by those IMFs, intermolecular forces pulling those water molecules together. So organizing into restrictive phases, that just means going from a gas to a liquid or from a liquid to a solid. More restrictive means that they can move less, right? So organizing into those restrictive phases causes the release of stored energy, which is an exothermic process. So think about it this way. I'm going to say that for the next slide, actually. Makes more sense. So this plateau ends again when all those particles have changed into whatever the phase, into the solid phase in this case, as you see this curve here. So same thing, you're cooling this down, get to a point where you hit freezing point, and then both solid and liquid are present until you slowly are getting more and more and more solid until this point where you have all solid, and then you can decrease the temperature even further. So again, we'll look at this a little closer. Temperature is decreasing, and then it actually drops slightly below. The substance is cooled below enough to solidify those IMFs. And when it does, you get energy released, and that energy has to go somewhere. So it goes into the surrounding molecules and therefore increases the temperature again, right? And drops back down again, and then energy is released and it increases the temperature, and then it cools down and keeps going until all of your solid, everything is solid, all particles are captured. At that point, it can cool down. So as an analogy for this one, if you had water that you were trying to cool down, let's say you threw it in a fridge or whatever in your freezer, but you kept going in there and you kept throwing in hot rocks or hot stones, that energy, that as soon as that hot stone hits that water, it's gonna release that energy, and it's gonna warm up that water. And the same thing happens when those IMFs, when those intermolecular forces are, or those bonds are formed to form a solid. You're having to release that energy, has to go somewhere. That particle before was a liquid. It had energy. It was moving around a lot more than a solid, right? Just vibrating more and sliding past other ones. So it had more energy, and that energy has to go somewhere. So when that energy gets released, it heats up everything else around it. So yes, that will become solid, that particle, but it releases that energy and warms up everything else around it. And then you have to cool those ones down. And then one of them, releases a bit of energy, and it keeps going until, in this domino effect, as long as you're continually cooling it to the point where everything is solid. So the same thing happens at boiling point, going from a liquid to a gas. We won't go through all of that because it's the exact same process. You're going to be heating that liquid. It's going to go up slightly above the boiling point, and then because it's an endothermic process, it's requiring energy put in. That energy is going to go into that gas particle, which is going to take off, and so it's going to drop back down. And up and down, up and down, and up and down, all the way across until all that liquid disappears. You can boil away that entire pot. I don't know if you've ever noticed, or measured it, but you can't boil water really above 100 degrees Celsius, not without doing some special tricks and making it not just water. If you have a thermometer in a pot of boiling water, it doesn't matter how much you turn your heat up, it's only going to be at 100 degrees Celsius. That's max. Anything, those gases that are above it, yes, those can be hotter. Those will be over 100 degrees Celsius because they have more kinetic energy. The same situation happens for condensing a gas. That those particles have lots of energy, they cool down, and you get the same little zigzag going on until all of gas disappears, turns into a liquid, and then it can continue to cool down at that point. So these melting and boiling points are a characteristic physical property, and I want to pause or at least uh, take a look at this, what this means. And I've talked about this. I think I've mentioned characteristic physical properties before, but I want to make sure you know kind of what I'm talking about there. It just means that it's something that is unique. So if you take a look at this, so kind of unlike height, fingerprints do not change and are specific to the person. So your fingerprint is a characteristic physical property. It's unique to you. Um, so it's a physical property that's unique to a substance and that can be used to identify that substance. So when we talk about boiling point or melting, sorry, or yeah, melting point, boiling points, um, that is unique to that substance. It's completely unique. Um, Water has a bunch of characteristic physical properties, and one of the really unique ones, actually, that is actually that. Um, where is it? It's interesting because it's that water uh, decreases in density as it turns into a solid. Most things, not everything, but most things, uh, as they become a solid, they become more dense, right? And I did have that demonstration, which I think I showed you guys before, but I don't know if you noticed this. Let's see if I can. I've I've been trying to use FET a little bit today, and it has been really, really slow. I don't know why. It hasn't been working properly. So we'll let that load. We'll see if it works in a second. So what's actually happening is because, well, I guess we can just use this picture. That'll work. Um, Water molecules that are as a liquid are actually closer together. They can slip and slide past each other because of the shape that they're in, this Mickey Mouse type kind of shape. I guess it's not quite Mickey Mouse, but with the two hydrogens and the one oxygen. But when it forms into ice, it actually forms into these six-sided crystals. Six-sided, it sounds familiar. Maybe it is because you think of snowflakes. Snowflakes all have six sides, right? They're all uh, hexagonal, basically, although they have different points and stuff, but they all have six sides. And that's because ice forms a six-sided molecule. And you can see that they're more spaced out than the actual liquid is. Now, this is a minor point, except think about if it was the other way around. Think like most things are as they're solids, and we'll see if we can get into something here now. Can probably do this one. So if this was neon, for example, neon is a solid, and this is really cold. If I put this as Celsius, you can see it's 259 degrees Celsius. And as I heat it up, as it becomes a liquid, and there's a very, very small point for, I think neon has one of the lowest points at where it's a liquid there. It's probably liquid form there, about approximately, yeah. Yeah, we're kind of right in this area. If I increase my pressure a little bit. Not sure if I can. Oh, this is a phase diagram. We'll see this a little bit later. Solid, liquid, gas. Anyways, that point between liquid and solid is um, you can see when it goes to solid, if I cool this back down, those molecules fit really, really closely together, right? I think I need to lower my pressure. Should be. Okay, there we go. Yeah, they fit very nicely, very tightly. If I switch this to water, you can see water is forming larger. I'll get this above 0. There we go. So now when I get to a liquid form, they can fit tighter together. And if I cool it down again, you see that they spread out. Which is interesting. And then of course, when I heat it up to a gas point where you can watch the temperature increase here, right? Then they of course go flying all over the place with all their energy spinning around like mad. So you can break those IMFs. But the point I wanted to make was the difference between the liquid and the solids there. So looking at that, um, if our liquid was less dense than the solid, if the solid was more dense, that would be weird because we would actually have lakes freezing from the bottom up, because as the water would freeze at the top, it would sink back down to the bottom because it would be denser, right? So then you'd have it dropping down to the bottom of the lake, and then it would freeze, or then the top would freeze and it would sink down, and fish wouldn't be very happy, that's for sure, because the whole lake would be frozen from the bottom up. Um, Unfortunately, it does have some negative effects as well, such as if you try and freeze a glass bottle, it breaks because that water expands, especially if you don't give the water room to expand. So never freeze a glass bottle more than like 3/4 full, because as that water expands, it'll snap it. It'll break it. It's also why if you have a cottage or something like that, you need to empty out your water pipes before winter so they don't burst. Anyways, side note, but kind of important. So whatever the case, I was getting at that melting and boiling points, they're characteristic physical properties. They are unique. They are fingerprints of substances, and that is because molecules are all different sizes and they have different intermolecular forces. So if we look at these 3 examples here, you've got propane, butane, and octane. Look at the molecules, right? You got C3H8, C4H10, C8H18. These are getting larger and larger. And as they get larger, the melting point increases actually. Remember, this is a negative, right? So this is much colder than this is, right? And this is the melting point. This is the point at where propane goes from a solid to a liquid. And that is because as mass increases, these melting boiling points also increase because there's more intermolecular forces to work against. You've got a larger molecule, something like octane. It's much bigger. It's like twice as big as kind of both of these, propane and butane, almost 3 times as big as propane. And so there's more intermolecular forces to have to break, which means you're going to require more energy to break them. So your temperature is going to have to be higher to break those intermolecular forces. So just more intermolecular forces to work against, then the higher that melting point is going to be, and boiling point as well. So make sure you guys understand that concept, okay? That's going to be something that I'm sure I'll ask you at some point on a quiz or test. Okay, so ionic compounds typically have higher melting points than molecular compounds. That's another kind of characteristic of them, basically. So because of the way that they're laid out with this positive negative really close together, they have really strong IMFs, the intermolecular forces, holding the molecules together. As such, something like salt compared to sugar, salt is 801 degrees Celsius for their melting point compared to sugar, which is 160 degrees Celsius. So unless you have one really super strong oven, you're not going to ever melt salt in your kitchen but you can very easily melt sugar. 160 degrees, that's like lower than most ovens can even be set. So, which is a good thing. We want to be able to melt sugar when we're baking. Okay. So the last thing to mention here, so IMFs must be overcome in order for a substance to change state phases. Uh, if we can't overcome those IMFs, then you're not going to break from a solid into a liquid. And if you can't overcome them from going from a solid to a gas, well, you're just going to stay, or sorry, from a liquid to a gas, you're just going to stay at that liquid, right? The greater the forces between the particles, the more energy is needed to overcome these forces. And so that's what we were talking about. Different kinds of molecules as well as size of molecules makes a difference about for those melting points and boiling points because the IMFs are stronger or weaker. Greater the IMFs, the higher the melting and boiling points. That is the takeaway there. So, can you explain this plateau of heating and cooling curves, making specific reference to IMFs and exothermic and endothermic? And then can you define melting and boiling points in terms of intermolecular forces and particle size, how they are affected by those two things? Okay, that's it for today. And yeah, we'll see you guys soon.